Two transformer cores, two coils of wire. Do you think we can make a magnetic amplifier and a 2-bit computer memory out of them? Well, let's try. So these two transformer cores are identical to the ones we used on the EM chain in the previous video. They're simply a standard off-the-shelf toroidal transformer with a 120 volt winding and a 30 volt winding. And I've taken a fair amount of care to make sure the polarity of the 120 volt terminals is the same for both cores. So that means the white wires correspond to the same side of the coil on both transformers, and similarly the black wires correspond to the same sides of the coil. And if I hook them together, well, we just have two plain old transformers that are now wired together. No big deal. But what I'm going to do is, in fact, make them a little bit more complicated, and using these two lengths of just plain old hookup wire, I'm going to add about 15 to 20 turns to each one of these transformers. So this is going to be real tedious. I guess the easiest way to do it will be to get about half the wire through the core, and luckily the people who make transformers have machines that actually do this. I don't have one of those machines. And this, by the way, is just plain number 14 household or residential wiring style wire that's used in most of the homes in North America. And you'll notice these coils don't have to be particularly neatly done. Okay, so there we have 20 turns of wire going through our toroidal transformer. And now I'm going to repeat the same thing with the other transformer using the white wire. We have 1, 2, 3, 16, 17. So that's 17. I guess we can put one more turn through it before we run out of wire. So that should be 18 turns. Oh, maybe one more than that. 19. Here we go. Well, that's not very much wire to work with. We'll just make it a little bit less. And I think what I'll do is remove a few turns from this one so that we have them absolutely identical. And if I did everything right, these two coils, this coil and this coil, have exactly the same number of windings. And what we will do is we will hook them up together. We'll power them together, I should say. And we'll measure the voltage on these two coils, and that'll confirm to us that I counted the windings correctly. And if there is about a 0.2 volt difference, we'll know that I miscounted. Okay, the power is on. And we'll use the good old voltmeter to see what the voltages are. So it should be probably around 3 volts or so, 4 volts. So this, the white one, is 4 volts almost exactly. What is the black one? The black one is almost 4 volts exactly. So I got it right. Let's just check the polarity now. The polarity should be identical. No, it shouldn't, because I have one of these cores flipped over. So I'm going to turn the core over. These two wires should have the same polarity as those two wires. And we'll test that by connecting these two wires together. And I'm just going to do it by clamping them together in a vice grip. There we go. And if I've got the polarities identical, there should be no potential across here. What do we have? We have essentially 0 volts, but each one of them is about 4 volts to the center point. All right. We have now achieved 2 transformers producing absolutely no voltage output. Well, isn't that a great video? I think we can make it more interesting than that. The way we're going to do it is we will disconnect the transformers from the AC power, and we will add a light bulb into the mix. And if we put the lead of the light bulb into now the AC power source and turn it on, we get absolutely nothing. What would happen if I were to short this black coil? Well, if we short the black coil, as we demoed in the previous video, it's equivalent to essentially shorting the 500 turn 120 volt coil, and the light bulb should go on. It does go on. Ooh, the light bulb is broken. Look at that. It just started oxidizing. So if we do that, the light bulb will burn out any second. Isn't that interesting? What we should also do is just take a look at the current flowing through this winding. And if I hold it here, the current, oh well, the light bulb just burned out. Please bear with me while I get another light bulb. All right, we have a light bulb. In fact, let's just sort of place it up here so you can see it a bit better. Let's try that one more time. What type of current would we have flowing if we shorted the black winding? About 11 amps. That's a fair amount of current, and certainly all it's really doing is using transformer action to take the probably half an amp or something current from the light bulb and convert it down to a larger current and lower voltage. But that's not what we came here to do. What do you think's going to happen if I touch these two wires together? Well, let's try it. Are you ready? 1, 2, 3. Absolutely nothing happens. Not a surprise, because just to remind you, there is essentially no voltage across these two wires. But what do you think happens if I take this 1.5 volt battery, dry cell as some people like to call them, and put it across these terminals that have absolutely no voltage across them? The light bulb goes on. Well, there you have it, a magnetic amplifier. I don't know if you could hear that, but the transformers also make quite a noise. You can hear the hum. All right, that's clearly an amplifier. This is a 60-watt bulb. This battery is about 1.5 volts, and it probably can pass maybe 5, 6, 7, 8 amps. In fact, let's test that. We can use this ammeter. It's a DC ammeter. It's producing about 9 amps. So we've got 9 amps coming out of the battery, And it is a 1.5 volt battery, but perhaps what we should do is see what sort of voltage is actually being delivered, because that's such high current the battery is not going to be able to deliver its full 1.5 volts. So the battery is delivering about 0.6 of a volt at about 10 amps, so about 6 watts. The bottom line is this battery is delivering 6 watts of power into these 2 wires, and all that power is really being turned into heat. But it's controlling, ooh, that's hot, a 60-watt light bulb. Isn't that neat? Now, these things were actually used probably before the 1950s or 60s, and I guess they were quite common in some equipment in World War II as a way of doing power amplifiers before we had high power transistors and before tubes that could operate on high voltages and high currents were fully developed. So it's kind of a neat technology. So what you might be wondering is, how on earth does this actually work? And we're going to look at that next. I've set up an oscilloscope, and the oscilloscope is showing us the voltage that's going into the primaries of our coils, in other words, the voltage over here. And it's also showing us the current that is passing through the circuit, through these coils. And I'm doing it with this box that has a 1 ohm resistor in series with the neutral wire of the AC plug. And by having a 1 ohm resistor in there, 1 ohm converts 1 amp to 1 volt, and that 1 volt is what's being displayed here. And you can sort of see that there's not too much current flowing through the coil. It is a bit of a funny shape, and we'll talk about it later. And anyway, if I take our battery, you'll notice that suddenly we have a vast amount of current flowing. And the current is, in fact, almost identical in shape and phase to the AC power going in, the AC voltage going in, and that's because it is a resistive load. If I remove the battery, the current fades away to nothing. What you will notice is that as I'm adding more and more current, you get those funny peaks occurring, and you can even hear the transformer making noises from those sudden bursts of current. And it's in fact those peaks that are really quite key to what's happening. So how does the magical magnetic amplifier work? Well, it's all based on what's known as the BH curve, which relates the magnetic strength or force field H to the magnetic flux B. Now, what is H and B? Well, I've just drawn part of Ampere's law down here, and the H field, the force field, is essentially equivalent to the current flowing through the wires in the coils of our transformer. The current, or the H field, is, if you want, what pushes the flow of magnetic flux. And that flow of flux is called B, and it's measured in Teslas. And it turns out that while in things like air and space, the one value is simply a multiple of the other value, when we're dealing with things like iron or steel, we end up with a funny nonlinear curve relating the two. And if we consider the H field, or this axis, to be current, it turns out that if we use Faraday's law and assume a sinusoidal type wave for the voltages, it turns out that the voltage that is induced in our coils is related directly to the strength of the B field. So if you want, this is current, and going up and down here, this is voltage. So how does that apply to what we've been doing? Well, when we have the transformer operating in normal operation, the transformer, or in this case really just an inductor, operates in this nice linear region where you have a small change in current producing a large change in voltage. And what that means is this large voltage, this large changing voltage, has to correspond to the 120 volts going into the coil. And if we work backwards, that tells us exactly what the current is that we see going into the coil at the same time. Now, if we start doing something to shift the operation from being around 0 to, let's say, moving up here, now what you can see happening is to get a correspondingly large voltage, such as on the peaks of our incoming AC waveform, you now need a very large current off in this direction. And that large current we saw corresponding to the peaks of our AC waveform, well, those were the peaks that we saw on the oscilloscope. Now, how do we move over from this region to this region? Well, that's easy. That's what the battery with the DC current did. It moved us from here over to here, and essentially what happened was suddenly the magnetic properties of the core had weakened significantly. The permeability, as we call it, is now much less, and much more current flows to be able to generate that 120 volts across the coil. In fact, so much current has to flow because we have a light bulb in series with the circuit. It never actually gets up to 120 volts anymore, and the coil looks pretty much like a short. So that's how the magnetic amplifier works. It's driving the coils in saturation. The only reason we have two coils is because we want the two DC coils to not be pushing any AC current, any AC voltage on the battery. So we use two separate transformer coils to make sure the AC voltage from the transformer cancels and the battery can simply push current along the transformer coil. All right, so that's all very well. You might notice that there is something funny down here. It's not quite a nice smooth curve, and it turns out along the very low magnetic field regions there is a little bit of nonlinearity, which is why when we look at the current going into the transformer coil, we do see some strangeness. It doesn't look like a perfect sine wave. But maybe more interestingly are these two dotted curves over here. And they correspond to, if we start increasing the DC current into our coil and into our iron or steel core, we start moving up this curve and getting a particular B field out. Now, if we start decreasing the current, it turns out that the field lingers and actually stays higher than it would normally do, even to the point where when we set the current to 0, we now have quite a strong magnetic field left in the core. And if we want to get rid of it, we actually have to apply a current in the other direction to bring it down to 0. And when it's down to 0 here, well, we're actually, at this point in the curve, we need even more negative current to produce a negative magnetic field, so the whole curve is shifted in this direction. And the exact opposite happens when we're going in the other direction. And this is called the hysteresis curve, and it is a source of loss in transformers because it turns out this region represents the amount of energy that's lost in every AC cycle that occurs from, again, what is known as hysteresis. But there are a number of interesting uses for this. Normally, in a transformer or an inductor, we use what are called soft magnetic materials, where these two curves are as close together as possible because we don't want to lose any energy to them. But if we want to make a permanent magnet, we make them far apart, and what that means is we have a very stable, long-lasting magnetic field when we remove the current. And that's how, in fact, you make a bar magnet. You charge it by passing a current through a coil around the magnet. Current goes away and we're stuck here. But in the old days, when they had to make computer memories and didn't have silicon chips the way we have now, they had another use for it, and that was this. You pass a big current through a coil and let the current then go to zero, and you leave either a positive or a negative magnetic field in that coil. And you can then examine it later and use that field to store some bits of data. And believe it or not, we can actually demonstrate it with our simple setup. So to turn this into a memory cell, it's actually quite easy. And all we're going to do is change this light bulb to this one, a much more efficient one that uses hardly any current. In fact, it uses so little current that it's on right now, even though our magnetic amplifier is off. Now, watch what happens when I start putting DC current into our transformer cores. Every time I touch it, the light gets brighter and brighter and brighter and brighter till we've pretty much got it as bright as it can possibly be. And in fact, it's drawing so little current here, we can hardly see it on the scope. I'm going to adjust the scope. We can see it a bit better now. But look what happens when I put the battery in backwards and just touch it very quickly. The light levels go down and then they start going up again. Turn it around. So we have one bright light level. We have a dimmer one and a dimmer one and a dimmer one. We have 4 light levels. 4 levels, 4 values corresponds to 2 binary bits. So this is in fact a 2-bit memory cell. Even maybe more bits if we can resolve the lower light levels. And you'll notice it starts getting higher and higher and higher again until we get the maximum. And just for fun, let's bring it down like that. And so you might be wondering what's happening. Well, what we're doing is we are passing some DC current into our coils, and that's bringing it up the curve or bringing it down the curve. And because of this ability for the magnetism to stay in the cores when we remove the battery, in fact, what happens is we've just shifted the whole curve up or down somewhat into the saturation region by leaving a DC magnetic field in those cores. And that's the principle of magnetic core memory. And we can just do that again. And this would be happening with the incandescent light bulb as well, except we don't normally see it because the incandescent light bulb uses 10 times the amount of current, and at these levels of current, well, we just don't see anything at all. Now you might be noticing there are some very weird shaped currents on the scope, And well, that's partly because we are operating in the partially linear and partially saturated region, and also because the electronics in this bulb are also doing some pretty weird things to the current depending on how the bulb is designed. So there you have it, a magnetic amplifier and a 2 or more bit magnetic memory cell. If you found this interesting, you might enjoy the previous video, which was an electromagnetic chain built using a number of almost identical toroidal transformers, and I'll put the link up so you can take a look. See you next time.